This is the top and the bottom. So I take the top here, the bottom here. The fox will be the attractive fox, right? From the top to the bottom or vice versa. So this is the fox. Then what is K? K is 9 multiplied with Q. Q is 40 multiplied with Coulomb, right? 40 multiplied with 40 over 2 kilometers. So let's convert the 2 kilometer into meter. So you have here 2000. Okay, this is all of the value. This one, right? This one is correct. But you have to have 3 significant figures. So let's say 9, 10.9 multiplied with 40 square over 2000 square. So this is the correct answer. 1, 2, 3 Newton. Okay, it's easy, right? It's easy to use. What is the electric force on the top charge? Rồi luôn Tiền cho thầy hỏi là có cần phải ôn lại về cái vector easy không? Có ai cần không? Có ai cảm thấy mình chưa chắc về cái easy không? Đúng rồi, bạn Thánh Đông hả? Trả lời downwards là đúng rồi. Rồi ok, nếu mà em ghi dấu trừ thì phải có trừ thì phải có chữ gì sau nữa nha. Lúc này có bạn ghi chữ gì đây mà thầy em phải xóa cái chữ rồi sau này. Rồi, cái này sai rồi bỏ đi ha. Đây, thầy kẹp lại rồi. Không thể sai. Có ai cân nhắc lại về cái vector không em?
Dạ có thầy ơi.
Dạ có.
Có ai nhắc lại chút xíu ha. Ok, bây giờ làm riêng cả. Okay, let's talk about the coordinate system. We have to use this in fast every problem, so it's important to repeat. I have a review of that. So, look at this. We have the Cartesian, right? Coordinate system. Okay, in this coordinate system, we have 2 axes. The horizontal one is normally called x-axis. The vertical one is called the y-axis. X-axis, y-axis. Okay, and normally we call the origin of that is O, right? O stands for the origins of the axis, a coordinate system. Then when we have a vector like this one, right? A red vector. Then let's call the vector is the fox. So we have the F vector. Normally this is the free vector. So we don't bound the end of the vector to any fixed point. It can be here, it can be here, somewhere on the plane. So we call it a free vector. The free vector or any vector has 2 components. So from this tab, we have the component of the vector. Component of the vector. What is this? So let's say I take the vector x for f, then I project this vector on the x-axis, right? Then I have here the fx component, fx component, and when I do it, For the vertical, I have the fy component. See in the two-dimensional, right? Fy component. So this vector must be a little bit bigger. Okay. So how can I define fx? Fs will be the magnitude of the force F multiplied with the cosine of the angle theta. Cosine of the angle theta here. Okay, what is the angle theta? The angle theta is this angle. The angle made of the Fox vector F with the horizontal x, and then the Fy is F sine theta. Okay, this is the two component of the vector. So I move it here. Then how can I write it together? I can write the Fox F vector is Fx I plus Fy j, which I and j the unit vector of the x and the y axis. Okay, so in this case, come back to the fox here. We have the fox, this is vertical and downwards. So I write it like f is equal to minus 3.6 multiplied with the million of Newton, but it's here along the y-axis. So I write it like minus 3.6, this one. Okay, is this clear now? Does you see the how we use the Cartesian coordinate system to express a vector? So let's come back to the problem here. We have 3-point charts lie along a straight line as shown in the figure, where Q1 is 6 microcoulomb, Q2 is 1.5 microcoulomb, and Q3 is minus 2 microcoulomb. The separation distances are D1 and D2. Let's calculate the magnitude and direction of the net electric force on A, Q1, B, Q2, and C, Q3. Okay, so let's start with the A question. You have 5 minutes for A. Again, the Coulomb's law is here. You can solve because we have the Zelo group already, so you can solve it on the paper and take a photos of that and send it to me, and I will show your answer, your solution to everybody on my screen. So I'm waiting for your answer, and our group. We have 41 members in the group already. Okay. Do you have the answer for that? So I will give you some hints. First one, let's draw the fox. Right? We focus on the Q1. So first of all, draw the fox from Q2. That x on the Q1. Let's say this vector. Okay. This is the fox, but is this correct? From here to here, this will be the repel, right? Repulsive fox. So this fox will be to the left. Then from Q3, the fox will be to the right. Right? I don't know which one is longer. I don't know, right? But when you look at the value here, this is the 6. It is 6 micron. This one is 1.5 micron. This one will be -2. And the distance here, E1 is 3 centimeter, D2 is 2 centimeter. So when you look at the values here, you can guess that the fox here is a little bit shorter, right? Than the fox to the left. Okay, I call this one F31. And this one will be F31, 21 and 31. Quốc Điền, did you get the two answer for question A and B? What it is? It is the two foxes F21 and F31.
Dạ, câu A em ghi nhầm.
Câu A là phần trên hả? 52 chấm là câu A hả?
Dạ không, 41.
41 hả?
Dạ,
Hướng về phía nào?
về phía tâm ạ, về bên
Về,
trái.
về bên trái, ok. Okay, so I will show you how we can use the fox here, right? To this problem. So let's say first of all, the fox F1 is equal to F21 plus F31. Okay, first of all, we have that. Then we have to define the first F21 and F31. First of all, F21, what is this? F21 is AE multiplied with Q1, Q2, over D1 square. Multiply with I. Right? But you can see the R21 is in the opposite direction of I, the unit vector, right? So I have to modify that by putting here the minus sign, because the R21 vector is in this direction. Okay, this is the R21 vector. I do it a little bit slowly so that you can understand it better, but later I will go faster, right? Okay, so this is for the Fox 21. Again, I copy it for the Fox 31. I'll just kill the 2 with the 3, and here 3. B. The distance between the Q3 to the the Q1 is D1 plus, right? So D1 plus D2. So I take the both of them in the square. And the direction is, again, this is the R31, right? R31. So I have to draw it like this. So again, here I have the minus I. Okay. So then when I put them together to the first formula, what do I get? I get here minus I everywhere. Ki, Ke is the same, so I put it out. Ke. Q1 is everywhere, so I put here Q1 out of the bracket. Then I had F here Q2 over D1 square and Q3 over D1 plus D2 square. Okay, so I change the position of the formulas. So let's use your calculator. Okay, Hong Phong get all the three answer for A, B, and C. Very good. You have to convert the distance from centimeter to meter, right? Okay. Then I have here minus 46.8 I. And you have to add the unit of the Fox here is Newton. So this is the final answer. Okay. Then you can do the same thing for the Fox that X on the Q2 and then Q3 for the question B and C at home. Okay. Do you have any question? Do you have any question? No? This is an easy one, right? So for the Coulomb's law, maybe
Dạ thầy ơi, cho em hỏi là
dùng hỏi đi.
dạ tại sao F31 lại là nhân cho trừ y vậy thầy?
Cái vector F31 này R á, cái R31 có phải nó ngược chiều với là nó từ 3 đến 1 không? Mình vẽ cái nào từ 3 đến 1 không?
Dạ dạ.
21 cũng từ 2 đến 1 không? Thì hai cái vector này nó cùng chiều mà nó ngược với y là nó hướng bên này này. Cái vector y là nó hướng bên này này. Vì cái trục x của mình bao giờ mình lấy từ trái sang phải ha, quen rồi, cái này là do thói quen thôi, được ha. Thật sự là cái này là ý thì sẽ rõ hơn. Nó là từ trái sang phải ha, mà hai cái ánh chàng này từ phải sang trái rồi thì mình phải lấy dấu trừ thôi, biết sao chưa?
Dạ dạ.
Đó, được chưa?
Dạ được.
Rồi, ok dùng. Okay, so let's have a look at another problem. Just a look. We need not to solve it now. For example, this one. You have to solve it at home. This one. We have here two small metallic spheres, and each one have the mass of m and the electric charge of q, 7.2 nanocoulombs, and the angle theta here is given 5 degrees with the vertical, right? How long are the string L? So in this case, the electric flux is the same as here, right? This is the repulsive flux. Okay, so the flux here, I can copy it down. The electric flux that acts on the right sphere is to the right, like this one. So this is from this lesson. But the two spheres here are at the distance d. I copy the formula here. So the distance between the two spheres is d, right? We don't know that at this moment. So we can apply the Coulomb's law to find the flux here. But when you remember back to the mechanics in the physics one, you can see that in this case we have a so-called equilibrium. What is this in Vietnamese? Equilibrium situation. Can someone tell me what does it mean in Vietnamese?
Trạng thái cân bằng.
Cân bằng, trạng thái cân bằng. Ok, không phải là vị trí cân bằng mà trạng thái cân bằng. Đức Vũ ha. Okay, what is the condition for an equilibrium? What is the condition?
Có hai condition là có thể là tổng hợp lực bằng không hoặc là tổng hợp lực bằng không.
Hai cái giống nhau mà, tổng hợp lực bằng không hoặc là tổng hợp lực bằng không.
Con nói lộn rồi.
Là mấy cái.
Dạ, tổng hợp lực bằng không với lại có moment này với lại tổng moment.
Chính xác. Vậy là nhớ giỏi rồi, lý một mấy điểm mà nhớ giỏi vậy.
Dạ mới học cơ kỹ thuật xong rồi.
Hèn chi rồi, ok. The conditions for the equilibrium is the sum of the foxes, every foxes. So I give here external fox, right, is equal to 0. So no next fox. And when we work with the solid object, we need to have the torque. So the sum of torque is 0 too, right? But here we use only the first condition. Tổng lực bằng 0 và tổng moment lực bằng 0. Thì ở đây mình chỉ cần dùng cái được rồi, dùng cái thứ hai cũng được, không sao, nhưng mà không cần thiết ha, tự vì là mình check cái này là chỉ có một điểm thôi, không phải là chắc chắn. Okay, so how many foxes are there that acts on this sphere? We have the fox, electric fox, right? Fe. We have
3.
okay. What are they? Electric fox.
Electric E. Trọng lực.
Gravitational force, right? Gravitational force. I put it in black. Okay, and then the
lực căng dây.
tension. The tension, right? The căng dây tension. Okay, so the sum of these three forces must be 0. Okay, so we have here a problem of a triangle. When I move this box to this one, I have a right triangle, right? So you can solve it easily at home by yourself. Okay, so let's take a picture of that, or I will copy it and okay, I copy it and send it in Zello group so that you can get it later. Okay, now this is time to talk about the field. What is the field? Right? Sorry, another point here is what happens when we have not a single charge but we have multiple charges. Then let's look back to the problem we solved with the 3 charges. Then we have to add every foxes that acts on a single charge. For example, here we have 4 charges, 1, 2, 3, 4. Then the fox that acts on the first charge will be the sum of the 3 foxes here. Okay, very easy. Sometimes when we have a situation like this one or the configuration like this one, we have the 2 positive charges that are fixed on this position and this position. Then we can somehow find a position between the 2 charges here, so that when we put a charge on this, the charge Q3, Q3 can be positive, can be negative, but the total force that acts on the Q3 is 0. So in this case, we have the so-called 0 resultant force, right? You can apply the Coulomb's law to find the position X here. So again, this is the homework. Do it yourself at home. I send it in the Zello group. Okay, Now we let's talk about the electric field. What is this? Electric field. So when we talk about the force that acts between the two charges, what happened to the environment or the space around only one single charge? Let's say in the plane here, what happened when I put a charge here? What happened? I know that when I put another charge here, right? The red and the blue one, the red charge here, then if they are in opposite side, positive, negative, then I say, okay, the force will be, the force on the red charge here will be this way. Okay, this is the attractive force. But what happened when I don't have this one? I don't have this charge. So is there anything at this point? The physicists say, yes, we have. At this point, we have the electric field. How can we recognize there is a field at this point? How? The answer is easy. Let's take a test charge, a very small charge, and put it here in this position. Then if the charge, we call it the test charge, if the charge is exerted by a force, electric force, we say, okay, at this point we have the field, right? So the definition of the field is easy. Let's take the force, and divide this force by the charge of the test charge. We call Q0 the test charge, right? The test charge. So let's say if we have a single charge here, then we can find the electric field at the point P here is to the right, horizontal and to the right. But what happened at the other position here? Then I can show you a simulation. That take me some second to turn on the simulation. Wait me for some minutes. You can also run the simulation on the LMS site. I show you. Simulation, when you look down on the chapter number 1, you can see some link to the simulation. Interactive simulation. Okay, click on that. It will lead you to the sites, and I will show you what happened on my screen. Okay, I got it. Now I stop the screen and define another new one. Okay. You can see my black screen. Okay. I can put here some charge, and when I want to measure the electric field at a point on this plane, I use the sensor here, right? I put it here. Wow, it's very large, right? I give only a single charge. When I put it here, I had the electric field. What does it mean? What does the role of the red arrow here? Can you see the red vectors? Okay, I say that it means here the E vector, the electric field vector, and normally we call it E vector. The E vector here have this magnitude and have this direction. This is a little bit stronger. This is a little bit weaker, and so on. But when I put a charge here, positive charge, then the charge here will be exerted by a force along this vector. When I put a negative charge here, this charge will be attracted to the source charge here. Okay, so when I test for all the place here, I click on this button, right, the checkbox here, then you can see everywhere in the plane. So let's test it here, right, the same like us. Let's test another point here, another point here, right? So you can see when we use the computer simulation, we can easily see in the bracket, see the electric field. Normally we cannot see that. We can sense that, we can feel that by using the test charge, but we cannot see the field. Okay, so let's come back to the presentation. Whenever we have the field E, then the force that acts on the charge Q will be QE. Right? So for this purpose, when we have any configuration, charge configuration, we can easily find the E. Right? This is for the single charge. When you have more than one charge, you can see, let's say, distribution of charges here, right? Then we use the integral technique. We divide the object here into many small pieces, very small pieces, and then we use the sum of every vector, electric field vector, and when the sum is infinite, we have a very large number of dq, then we move it from the limit of this sum to the integral. Okay, any question at this point? Do you have any question? So let's look at the problem. Problem is everything. 24. Electric field. 24. What is this? Okay, this is the problem for you to solve. Let's take 5 minutes, try to solve this problem. A small object of mass 3.8 gram and the charge of minus 18 microcoulomb is suspended, motionless, above the ground when immersed in the uniform electric field perpendicular to the ground. What are the magnitude and direction of the electric field? Is there any words that you don't understand? Suspended, maybe, right? Suspended, levitate, lơ lửng, suspended, lơ lửng, motionless, easy, right? Uniform electric field, what is this? What is uniform electric field? Can someone tell me what is this? Uniform electric field. You know the word in uniform, right? What is this in Vietnamese? Uniform. Đỗ Việt Lâm đây có những câu hỏi là làm lại chỗ này được không? Ok, cứ thử tí đã ha. Giờ mình đang làm cái này rồi xong quay lại. Uniform là gì vậy mẹ em? Uniform thôi, thầy hỏi thì uniform thôi là đồng phục ha. Nhưng mà trong trường hợp này thì uniform electric field là điện trường đều. Điện trường đều nghĩa là làm sao? In the uniform electric field, the electric field vector or the E vector everywhere in the fields have the same direction and the same magnitude. Okay, so let's say I have here a uniform electric field vertical upwards. So everywhere, right, in the plane, the electric field have the same direction like this. Okay, everywhere. Right? But if it is a case, I don't know, that have an example. Okay, so I have here a small object. I can tell it's at a small sphere here, yellow. It is suspended. It means the electric force and the gravitational force will be cancelled out. So first of all, this is the gravitational force. I rotate it. And this is the electric force, the red color. Okay, this is the gravitational force and this is the electric force. They have the same magnitude but in opposite direction. Okay, Đinh Thành Nhân get an answer already. Upwards. Okay. So first of all, the force sorry. Here, first of all, the force will be let's say I write like Fe plus Fg gravitational force is 0 for the equilibrium, right? Then I can come to the result that Fe is minus G or minus mgj when I take the y coordinate upwards, right? Then I can use the definition of the electric field. The electric field at this position is equal to Q multiplied with P, where E the field. Okay. Then from the two equations here, we can easily get Q or E. Now I want to have E, then I have E is V equal to minus mgj over Q. Okay. Can you see how I play with the formulas like this? Okay, so when you substitute the values, numerical values here, what do you get? I have here minus Jm is 3.8 gram. So I have to multiply that with the power minus 3 2000 to 10. Okay, multiply with J, multiply with 9.8. Remember, we have here 9.8. And you can add the unit into the formula, no problem. Q here is minus 18 micro. So you have to convert coulomb to microcoulomb. Okay, and J. Nhân, you changed your mind. So what is the fox? Minus. I have a mistake here. Fe is minus Fg, but Fg itself is minus, right? So I have here twice of the minus sign. Twice of the minus sign, right? Fg, gravitational force itself is minus, right? So I have here a minus sign. So here in my equation, I don't have any minus here anymore. Then I don't have the minus sign here on the numerator. Okay. So You see downward, right? So you can copy it down in your notebook. Please try to write down so that you have the feeling how to write physics equation. The feeling is very important, right? When you solve problem, you get the same feeling, then you can get the correct answer easily. Okay, so let's calculate that. 3.6 multiply with the power minus 3 multiply with 9.8 over 18. Okay, you get this answer. So minus 2070. Okay, can you see that I rounded the value here in the answer? 2068.88 is rounded so that I get only 3 significant figure. One is the number 2, 2 is a 0, and the third one is 7. This is not significant. The last 0 here isn't significant. Okay, so this is for this example. Do you have any question? Yes or no? So I got a question, a demand from someone here. I missed the name, but he asked me about this one again. This one, it is who give me the answer? Ok, Đỗ Việt Lâm đó. Việt Lâm hay là Việt Lãm? Hiểu cái gì vậy? Lúc nãy em hỏi cái gì vậy lắm? Em hỏi cái sống hả? Ok, Việt Lâm, ok. Now let's come back to the integral. When we have an object like this, we call it a continuous charge distribution. It's a very interesting but difficult concept, continuous charge distribution. Let's say, do you eat the dragon fruit? Dragon fruit? Do you know what it is? Trái thanh long, right? So when you want to put the core, the black small, then you can find it everywhere inside the fruits, right? Then let's say they are charges in our situation. So let's take all of the vector here and make it a sum of that. This is difficult in this case, but fortunately we take easier situation, right? Very easy. For example, this is the formula only. When we have the volume charge density, we have the surface charge density, or linear charge density. Imagine in this case we have the line. It can be the straight line or the curved line, curvy line, no problem, right? But the charge will be distributed along this line. So let's say I have the line here. I have the line like this one, right? And the charge is everywhere on the line, right? When we have a surface, let's say I have a oval here, on an oval disc or a round disc, then the charge will be everywhere on the plane of the disc here. Then we have a surface. Then if we have a box like this, right, a box, then the charge will be everywhere inside the box. At any point inside the box, we have a charge. So we have a so-called volume charge density. Okay. Then if the charge is distributed but evenly, what is the meaning of evenly? Can someone tell me? Evenly. Chân quốc điền là chân quốc điền hay quốc diện vậy? Evenly là gì điền? Alo, điền đâu rồi? Evenly là gì điền?
Dạ quốc điện.
Hả? Evenly. Điền hả?
Điện.
Em là điền
Điện.
hay điền? À
Điền.
rồi, điền. Evenly là gì điền?
Dạ đều.
Đều. Nó giống cái chữ gì lúc nãy?
Giống chữ
Uniformly. Ok.
Dạ.
Đấy ly là vì nó là adverb. Thì uniform có nghĩa là khắp đều, mọi nơi là đều như vậy, không có chỗ nào nhiều hơn ít hơn. Đấy. Nhưng mà một cách bình thường á, thì cái này có thể là hàm. Ok. Rho, sigma and lambda can be a function of position of x, y, z in the three-dimensional space. Okay, so let's look at the problem. An example. I have here a dot. Can you see my full screen? Can you see the screen here? With the red point. Hello. Đây thử chiếu cái này lên coi có thấy không nhá. Hình như là không được phải không? Ok. Từ vì cái này nó không cho thôi được rồi. Okay, this is the problem for as an example. You have here a rod and the charge is distributed uniformly on the rod. Okay, and how we can find the electric field at the point P here? In this case, P is the origin of the coordinate system XY. Okay, so we have here OXY. How can we calculate the electric field at the point P here? using the integral technique. Okay, first of all, we have to define the tiny piece of charge we call as dq. A very small piece, we call it dq. Okay, so I take the dq as a small piece of the length dx here. I cut a small piece here with the length dx and I call it dq. Okay, what is dq? Because the rod here is uniformly distributed, right? So I have dq is lambda multiplied with dx, length, as the definition here, right? Lambda is q over L, so q is lambda multiplied with L, the length, but the length here is dx, so I have here dq is lambda dx. Okay, then I define the dE at this position because of this dq. So I have here dE. The magnitude of that is dE is k at E dq over the distance d squared. Okay, because the position of this dx is x from the coordinate system. Then I will later substitute d here with x. What is it that the magnitude? What is the direction? If the rod is positive, then the electric field will have this direction, right? So I can add the vector here like this. And instead of d, I write x. Okay, it is clear. dE is ke dq over x I, the unit vector. But because this is a positive, so I have to use the minus sign here. So I have to modify it again. Instead of I have to use minus I. Remember the R vector in the previous problem, right? Minus I, because it's in opposite direction with I. Then we have to take the integral of that. So let's copy it here. I think I have another slide here. Okay, dE. This is from the previous. This is from the previous page, right? Now I take only the magnitude of that, so I ignore the minus I here in this formula. Then I have this one. Substitute things to that. I have the range to calculate the integral is from a to L plus a. Why? Let's come back to the figure here. The rod is from A to L plus A on the x-axis, right? A here, the length L, so here is the coordinate of this end is A. Another end here is L plus A. So I have the range of the integral is from A to L plus A. Okay, then when I look do the integral table at the end of the chapter. I have integral of dx over x squared is minus 1 over x. Substitute the range a and l plus a to that. I get finally I get this one. Okay. Or maybe more simpler, I get this one. So you see how we can use the integral technique to find the electric field created or up an object. In this case, the object is simple. You see a straight line or a rod. Later, we can have, let's say, a little bit complicated, right? The ring and maybe the disc or the sphere and so on, right? But is it enough for today? You were working very well in this class. I'm very happy. When you have question, you can ask me in the Zello box, Zello group. You can send me questions via the Zello group, right? Or you can write me email, but from the Zello it's easier for me to read and to answer you. So we stop the class now and see you next week on Monday again. Okay, so have a good day.
Goodbye, teacher.
Goodbye and
Bye, teacher.
have a nice lunch.
Goodbye,
Goodbye,
teacher.
teacher.
Bye, sir.
Bye.